Hello everyone, welcome to the series on finite element analysis. In this series, we'll be learning numericals on 1D spar or rod element using finite element analysis. So let us start with the first chapter, matrix analysis of 1D spar or rod element. In this chapter, we'll be learning the basic concepts related to finite element analysis of 1D spar or rod element. So let us consider one-dimensional element shown in figure, which has two nodes as shown in figure. So this is node number 1, node number 2, and each node has 1 degree of freedom. Let us take L1 as the length of the element. U1 is the displacement at node 1. U2 is the displacement at node 2. F1 is the force acting at node 1. F2 is the force acting at node 2. A is the cross-sectional area of the element in millimeter square. E is modulus of elasticity, also known as Young modulus, in Newton per millimeter square. F1, F2, as we have already said, forces acting at nodes 1 and 2 respectively, and U1 and U2 are the displacements at each node 1 and 2 respectively. So let us calculate the total degree of freedom of the system. So total degree of freedom of the system N is calculated as DOF per node multiplied by number of nodes. So here we have DOF per node as 1, whereas we have 2 total number of nodes. So therefore the total degree of freedom of the system is 2. So this total degree of freedom of system decides the size of element stiffness matrix, which is 2 by 2 in this case. The stiffness of the element is now calculated as K is equal to area into Young modulus upon L. So let us refer the figure back. So from this figure, we can write F1 is equal to K into U1 minus U2. This comes from the basic equation of the spring force, that is K into delta X. So at node 1, what we have, U1 is stronger as compared to U2. Okay. So the change in the deflection will be U1 minus U2. So K into U1 minus U2 will give us the force at node 1. Similarly, we can calculate force at node 2, which will be equal to K into U2 minus U1, whereas U2 is stronger or more at node 2 as compared to U1. So net deflection or deformation of node 2 can be calculated as U2 minus U1. So this is what the basic formula we used. Spring force is equal to K into delta X. So rearranging these two equations, what we have is that F1 is equal to K into U1. If you open this bracket, we have K into U1 minus K into U2. Similarly, for F2, we can write F2 is equal to minus K into U1 plus K into U2. Now in matrix form, we can write matrix of F1, F2, that is equal to matrix of K minus Kk into matrix of displacement, that is U1 and U2. Or in short, we can write matrix of F is equal to matrix of K into matrix of displacements Un. Now the order of the force matrix is n into 1, whereas the order of the stiffness matrix is n by n. As already we have discussed that the total degree of freedom decides the element stiffness matrix. So here you can see the order of the element stiffness matrix is n by n, whereas the order of the displacement matrix is n into 1. Okay, so F is known as element force vector, K is known as element stiffness matrix, and Un is known as element displacement matrix. Now let us learn how to assemble these two one-dimensional elements. So let us consider two one-dimensional elements as shown in figure. This is element number 1, element number 2. Okay, which has node 1, node 2, and node 3. L1 is the length of element 1, L2 is the length of element 2. U1 is the displacement at node 1, U2 is the displacement at node 2, U3 is the displacement at node 3, F1 is the force at node 1, F2 is the force at node 3. Okay, so element 1 and element 2. Now the nodes 1, 2 and 3 are known as global node numbers, whereas the elements, when we visualize individually, the nodes are always labeled as 1 and 2. So this is known as local node numbering. So for example, for element 1, we have, if we consider this individually, we'll have the two node numbers 1 and 2. Okay, so this will be the local node numbers. Whereas again for element number 2, when we consider it individually, we will have the starting node 1 and this is end node 2. So 1 and 2 will be always constant when we consider each element individually. So therefore, this is known as local node numbering. Whereas 1, 2, 3, okay, these are marked as considering system as a whole, and therefore these node numbers are known as global node numbers. Now let us consider element number 1. Now remember the force acting at global node I of element j is represented by Fij. We are going to use this concept when we draw a free body diagram for each element. So let us consider element number 1, okay, which has stiffness K1, then node number 1 and 2, okay, which are the global node numbers, please remember. Then L1 is the length of the element 1, then U1 is the displacement at node 1, U2 is the displacement at node 2. Now let us mark the force acting at node 1 by using the concept Fij. Okay, so Fij for node 1, how we can write? It is the force acting at global node I. Okay, so global node number is 1. Okay, element J, element number is 1. So we'll have F11 as a force acting at node number 1. Similarly, we can write for node number 2 as F21. Okay, so this is node number 2 of element 1. So therefore, force acting at node 2 will be F21. Now the load and displacement force relationship or global relationship for element 1 can be written as F11 F21, that is equal to K1 minus K1 minus K1 K1 into U1 U2. Okay, let us mark the node numbers for each column and rows. Please remember this concept is very important. When we write this global relationship, we must mark the global node numbers at the top of each column as well as each row. Please remember each column belongs to each node. So here you can see this column, when I talk about the stiffness matrix, it belongs to node number 1. Okay. Similarly, this it belongs to node number 2. Similarly, each row belongs to each node. So first row belongs to node number 1, whereas second row belongs to node number 2. Now let us consider element number 2. Okay, so this is element 2, which has stiffness K2. Again, it will have global node numbers as 2 and 3. Okay, L2 is the length of the element 2. U2 is the displacement at node 2. U3 is the displacement at node 3. Now let us mark the forces acting at node 2. So it will be what? It will be now Fij. Okay, so I is what? The node number. So it is 2, isn't it? And element number is 2. So it will be F22. Okay, similarly here, node number 3, okay, element 2. So it will be F32. Okay, so this is what the free body diagram of the element number 2. Now similarly we can write load displacement force relationship or global relationship for element 2 as F22 F32, that is equal to K2 minus K2 minus K2 and K2 into U2 U3. Okay, so in short we can have matrix of force matrix, that is equal to stiffness matrix for element number 2 and displacement matrix for element 2. Let us mark the column numbers and row numbers. So since element number 2 has those numbers associated with it as 2 and 3. So therefore the column numbers will be marked as 2 and 3. Similarly, rows will be marked as 2 and 3. Okay. So let us now see the assembly of these two elements. Now total degree of freedom of the system n will be DOF per node multiplied by total number of nodes. So here we have one dimensional system. So DOF per node will be 1. Total number of nodes are 3. So therefore 1 into 3, that will give us total degree of freedom of the system n is equal to 3. And therefore the size of the global stiffness matrix will be 3 by 3. So let us now write global load and displacement force relationship. Okay, so adding equation 1 and 2, what we have is, so we are adding the matrix equation 1 and 2. So we have F11. Then for node 2 we have two forces F21 and F22. And for node 3 we have single force F32. Okay, the global stiffness matrix will be K1 minus K1, okay, then 0, then minus K1, K1 plus K2, minus K2, and third row will be 0 minus K2 and K2. Okay, so while writing this global stiffness matrix, you have to take search combination for column number 1 and row number 1. Okay, so let us go back and see. So here you can see 1 is what? K1 we have. Okay, column number 1, row number 1. Similarly, if you want to write the second, it will be minus K1, row number, column number 2, row number 1. Similarly, we can write for the others. Okay, now F11, that is the force acting at node 1, that is equal to the external force F1. F21 plus F22, the total force acting at node 2. At present, we don't have any force there, so it will be equal to 0. And F32 will be force acting at node 3, that must be equal to the external force, that is equal to minus F3. Why minus side? Because it is acting towards left. The sign convention is that if the force is acting towards right, it is considered as positive, whereas if the force is acting towards the left hand side, it will be considered as negative. Now since F3 is acting towards left hand side, we have considered it as a negative force. So therefore, final equation will have F1, that is the net force acting at node 1. At node 2 we do not have any force, so 0. F3 is the force acting at node 3. That will be equal to K1 minus K1 0. Then minus K1, K1 plus K2 minus K2. And then third row is 0 minus K2, K2 into the displacement matrix. So in short, we can write the matrix of F is equal to matrix of K into the displacement matrix. This equation is known as the global load stiffness displacement relationship, or in short, we can call it as the global relationship, where this F stands for global force vector, K stands for global stiffness matrix, and UN stands for the global displacement matrix. Thank you. In the next video, we'll be seeing how to solve the problems based on this concept. If you like the video, like, share, and subscribe the channel.